All right, welcome to today's lesson. We're going to be learning today about inclined planes. All right, so learning targets. Once again, we're basically just going to be learning how to solve more Newton's laws style problems. These ones will occur on slanted surfaces. Okay. So here's the deal. So in our last video, we learned how to deal with problems like this, where you had some sort of object, and then you had a force acting at some weird angle, right? Like sort of the classic lawnmower problem. All right, and so what we ended up doing was this. Because the force didn't lie along either of our axes, we took that force and we found the components, right? So to be clear, when I talk about our axes, what I'm talking about is, well, the motion is going to occur along this axis, right? So we call that the x-axis. And in most of these problems, there is no motion along the y-axis, right? But the issue was that this force here didn't lie along either the x or the y-axis. And so what we did was we took that force and found the components, and we replaced this force with an x component and a y component, right? Okay? And so that way all of our forces lie along our axes. Okay? So, but here's the deal. There's nothing magic about those coordinate systems. There's no reason why we have to use an x-axis that points perfectly horizontally or a y-axis that points perfectly vertically. All right? So what we're going to be doing this section is this. We're going to be solving these inclined plane problems. So we're going to have an object like this box that's sitting here, okay? And it's on an inclined plane. All right? And so what's going to happen is the box is going to either, if we don't touch it and there's no friction, it'll slide down the ramp. If there's friction, then it'll either not slide at all or slide down the ramp. Or maybe, maybe we're trying to push the box up the ramp, okay? But regardless, most of our motion is going to occur along an axis that runs this way, right? So what we're going to do is we're going to change our axes systems, all right? So instead of using the traditional x and y axis system like we usually do, we're going to use this as our axis system. Okay? And so let's give those two axes new names. We don't want to call them x and y because x is usually reserved for an axis that runs horizontal and y is usually vertical. So instead of calling them x and y, what we're going to do is we're going to call our axes parallel and perpendicular. Okay? And what this does is it ensures that our motion occurs on one of our axes, in this case the parallel axis, all right? And it simplifies a lot of the calculations, all right? But there is one problem, okay? And our big problem is this. So I don't like how fat I drew these axes. So let me draw these again real quick. So here's my two axes. There's a parallel axis and a perpendicular axis, right? But the biggest problem is gravity, right? So my force of gravity the force of gravity doesn't go, oh, well, Mr. Hecker put that box on a ramp, so I'm going to pull sideways, right? It's not like gravity knows to pull down the ramp. Gravity still pulls straight down along our old y-axis, right? So Fg, all right? So in the same way that we took the force from the lawnmower, oops, wow, what is going on with this? In the same way that we took this force here and found the components along the x and y axes, we're going to do the same thing over here. We're going to take our force of gravity and find the components of that lie along the perpendicular and parallel axes. All right? So here's the deal. This problem tells us that the plane is inclined at 30 degrees. Okay? When you talk about the incline of a plane, when you give the angle is always assumed to be off of the horizontal. So that means that this angle here is 30 degrees, which means that this angle here is 30 degrees. You can do a little bit of geometry to show that that means that this angle here is also 30 degrees. I'm going to skip that right now, but you can hopefully just kind of see that those angles look like they're about the same size. All right? And so when we draw our triangle, it's going to be a right triangle, but how do I want to say this? Instead of the hypotenuse is going to be the force of gravity, okay? And then the two components are going to point perpendicular and parallel. All right, so let's draw on the rest of our triangle. So we're going to have one component that points along the perpendicular axis, Fg perpendicular, and we're going to have one component that points along the parallel axis, Fg parallel. Okay? What I want you to notice is the right angle is here. Okay? So to be clear, this side here is parallel to the ramp, okay? And this side of the triangle is perpendicular to the ramp, okay? So, and then our hypotenuse, I guess since we're in highlighting mode, our hypotenuse is going to be this guy, okay? So, if I lost you a little bit here with the geometry, take a deep breath and go, it's going to be okay. Because here's the deal. Every single time, it's going to be the same setup, right? Because gravity always pulls straight down, and our incline is always going to be at some angle, okay? And so you can do a little bit of trig, which I'm going to skip because this is physics, not math class. And what you discover is this. If you calculate the component of the force of gravity that is parallel to the axis, that's this side here, right? The yellow side, right? That's the opposite, the side that is opposite the angle, and so we use the sine of theta to find it, okay? And similarly, if you want to find the perpendicular component, you use cosine, okay? So, here's the deal. This is big concept, all right? Let me erase all of this. So, here's how you solve inclined plane problems, okay? You can read the problem. 40 kilogram box is placed on a frictionless plane inclined at 30 degrees. All right, and your train of thought should be this. Oh, I've got a box on an inclined plane. I should find the force of gravity, right? That's always your first step, is find your force of gravity, right? So we're going to go, all right, force of gravity. Oh, well, that's m times ag, right? Do you know what? I'm going to do this in a different color. Sorry. And you'll see why in a second. All right, so I'm going to find my force of gravity. Fg equals m times ag. So let's see, the mass of my box was 40 kilograms. Acceleration of gravity is negative 9.8 meters a second squared. And so that gives us negative 392 newtons, right? Okay? And so what I should be thinking is, oh, but that force of gravity is down. But my object is on an inclined plane. So I don't want to put this force in my free body diagram. So in the same way that when you have a force at an angle, you replace it with the two components, right, that lie along your axes. We're going to do the same thing with our force of gravity, okay? So what I'm going to do is, over here, I'm going to go, oh, well, let's find our Fg parallel. This is the component of the force of gravity that's parallel to the axis. Oh, well, that's just Fg times the sine of theta. So for us, it's negative 392 newtons times the sine of 30 degrees, and it gives you negative 196 newtons, all right? And so the idea is, that's the force that pulls the box down the ramp, Fg parallel, negative 196 newtons. And you can always draw it there, because the force of gravity, I should say the parallel component of gravity, will always pull the box down the ramp, okay? And then similarly, find some room on your page and find your, find your Fg perpendicular. This is the component of gravity that pulls the box into the ramp. So that's Fg times the cosine of theta, which is negative 392 newtons times the cosine of 30 degrees, which gives us an answer of negative 339.48 newtons. All right, that's the component that pulls down into the ramp. Okay, so what did I just say? 339.48 newtons. Okay, so that's that. All right. So what I want you to understand is these two vectors that I just drew here, the blue one and the red one, represent the force of gravity. Okay? So if I used vector addition and added these two components up, watch what happens. So I got to place them head to tail, right? So I'm going to take this vector, I'm going to take the whole thing and move it down here. Oh, fail. There we go, something like that. And those two vectors are now head to tail. They're at a right angle, and they represent this. Okay, so the whole point, sorry, I had to pause it there. Somebody came into the room. So the whole point is what we're doing is we're replacing this green force of gravity here with the two components, okay? So ultimately what you end up just putting in your drawing is just the components. Okay? All right, so continuing on. All right, so there's one other force acting on this thing. So let me kind of clean up some space here. You got to make sound effects or it doesn't work. All right, so there is one other force. All right, so my motion is going to be down the ramp in the direction of the blue arrow. Okay, this red arrow though is it's like pushing the block into the ramp, right? So here's the ramp, and the normal force is kind of pulling down into the ramp. Okay, and so the idea is the ramp is there and it prevents it from moving this way, and so we have a normal force. All right, now that normal force, you guys, remember the word normal in math means perpendicular. All right, despite the fact that I did a rotten job drawing this, our normal force is always, without exception, perpendicular to the surface that's exerting that normal force. Okay, and so for us, it's perpendicular to the ramp. All right, and because this is a first-year physics course, it's in this class will always be exactly big enough to cancel out this perpendicular component of gravity. So this is positive 339.48 newtons. Okay, notice it's a little bit less than the weight, right? Because it's no longer supporting all of the weight, right? Because it's going to move down the ramp. Okay, but it does provide enough force to prevent it from going into the ramp this way. Okay, so that's that. And so now we can find our net force, right? So our net force here is going to be, well, this and this cancel out. So our net force is just Fg parallel in this problem because it was frictionless. Okay, so now we can find our acceleration. Acceleration is net force over mass. So our net force is negative 196 newtons. The mass is 40 kilograms. So divide this and you get negative 4.9 meters per second squared. Okay? So that is how you do that. All right? I was going to say another thing and I just lost it. Oh, I know what I was going to say. All right. Also, let's talk real quick about positives and negatives. All right? I will usually make down the ramp and into the ramp negative. So my coordinate system is always going to be parallel, perpendicular, negative, negative, positive, positive. Okay? So there you go. All right, so let's try another problem here with some numbers. Okay, so here we've got a 30 kilogram box sliding at 6.5 meters a second when it begins going up a ramp inclined at 25 degrees. Coefficients of static friction are blah, 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 blah. Okay, so let's draw this. So here we go. We've got an inclined plane with a box on it. The problem tells us that it's a 30 kilogram box. All right, my train of thought is, oh, I've got a thing on an inclined plane. I'm going to find the force of gravity. So 30 times 9.8 gives you negative 294 newtons. And then I'm going to go, oh, but because it's on an inclined plane, I don't want to draw this. I want to draw the components. So let's find our perpendicular and parallel components. Okay, so I usually do parallel first, not for any reason. So Fg parallel, remember that's just Fg times the sine of theta. So here's my Fg. My theta is 25 degrees. 25 degrees. All right, so I'm going to get negative 294 times the sine of 25 degrees. And I find out that my Fg parallel is a number written on this piece of paper, negative 124.25 newtons. So let's put it on our drawing. Fg parallel, negative 124.25 newtons. Okay. Similarly, I can find my Fg perpendicular. That's just Fg times the cosine of theta. So same numbers, different angle, and you end up getting negative 266.45 newtons. So let's put that on our drawing. Okay, notice my gravity points down the ramp and into the ramp. So Fg perpendicular is negative 266.45 newtons. All right, now, I know it's not going to move into the ramp, so I can go ahead and put in my normal force. That's going to be positive 266.45 newtons. All right, so that is that. Now, what other forces are there? Well, we got friction, right? I gave you the coefficients of friction. All right, so let's do this. Let's move this stuff out of the way. Where do I want to put it? I'm going to shrink it and then put it down here. Okay, All right, so now we can take a second and find our forces of friction. So our force of friction static max is our coefficient of static friction times our normal force. So here's my normal force, and my coefficient of static friction is 0.5. Okay, and that gives you 133.23 newtons. All right. I actually don't need that yet because the problem has told me that the box is already sliding. Okay, so let's go ahead and find the maximum force of kinetic friction. I said maximum, I shouldn't have. Let's find the force of kinetic friction. There is no max, right, with kinetic. All right, so what do we get? 0.4 is our coefficient. Normal force is still 266.45. So multiply this and you get 106.58 newtons. Okay? All right, so put that down here. Okay, so we've done kind of a lot of legwork here, so let's figure out what's going on here. So the problem tells us that the block is sliding up the ramp at 6.5 meters a second. So I'm going to have to move my drawing here. We're going to run out of room. So let me do this. Move that over a little bit. Okay, so since the block is sliding up the ramp with an initial velocity of 6.5 meters a second, that means we're going to have friction pulling down the ramp. What kind of friction? Oh, kinetic, because it's already moving. And since it's moving up the ramp, the kinetic friction is going to go down the ramp. So it's going to be negative 106.58 newtons. All right. And it's just sliding, so there's nothing pushing it up the ramp. So I think that's it for part A. So for part A, our net force is, well, normal and perpendicular cancel out, right? To put a point on it. This force and this force are going to cancel out. All right. And so my net force then is just going to be Fg parallel plus my force of kinetic friction, right? So that's negative 124.25 newtons from parallel, negative 106.58 from friction, and so my net force is negative 230.83 newtons, and so now I can find my acceleration by doing net force over mass. Remember, your mass is 30 kilograms. You get an acceleration of negative 7.69 meters a second squared. And now question A wants to know how far the box is going to go up the ramp. So what we know is our VI is positive 6.5 meters a second. Our final velocity is going to be 0. We're looking for our delta x. So we can use this guy, 2a delta x equals vf squared minus vi squared. And solve for delta x. And you get, I'll let you guys do the math, you get 2.75 meters. All right, so that is part A. Okay, so, oh shoot, that's not what I wanted to do. That's what I wanted to do. All right, part B. Part B says, once it gets up there, will it slide back down? And then, if so, how long will it take to slide back down? If not, how much force does Roy need to make it slide down in 1.5 seconds? So first of all, let's figure out if it slides back down. All right, so let's make a new free body diagram. We've got a new scenario, so new drawing. All right, but a lot of it remains the same, right? Let's see, I've got my mass. My Fg perpendicular is still going to be negative 266.45. My Fg parallel, oops, my, oh my gosh, Fg parallel, why do you hate me? Fg parallel is negative 124.25. We're going to have a normal force of positive 266.45. All right, so once it stops, that's my deal, right? All right, now, so gravity's pulling it down the ramp, okay? Does it go back down the ramp? Well, I don't know. It stopped here, and gravity's trying to pull it down. So at this point, we should ask ourselves, can static friction prevent the motion? So in order to prevent the motion, we would need an upwards force of 124 0.25 newtons, right? Cancel that out. And according to our calculations, we've got 133 newtons. So we could just put in a static friction force here of 124, and then we'd be done. We would say, oh, it doesn't move, okay? But the question asks us to do something else. It says, if not, how much force will Roy need to make it slide down in 1.5 seconds? Okay, so our question is, find the force of Roy under these circumstances. So we want it to slide down in 1.5 seconds. To slide back down, it's going to have to go back down that 2.75 meters it just went up from an initial velocity of 0. So if you use this equation, we know the everything here except acceleration. So if you solve for your acceleration, you end up getting negative 2.44 meters a second squared. Okay? So we are almost done here. I don't know what I'm at on my time, but we're getting there. So that's my acceleration. So what I'm going to do now is I'm going to find my net force. So net force is mass times acceleration. So the mass was 30 kilograms. Acceleration is negative 2.44 meters a second squared. Multiply this and you get negative, is that right? 73.3 newtons. All right, so now what other forces act on this thing? Well, we're trying to make it slide down the ramp. So we've got a force of friction. It's sliding, so it's kinetic, and we already decided that it was 106.58 newtons, right? Notice my friction is now going up the ramp because the box is going to be sliding down the ramp. All right, and we're trying to find the force of Roy. So we're just about done here. So here we go. Let's see. Once again, these two guys cancel out. These cancel out. So my net force here is Fg parallel plus force of kinetic friction plus force of Roy. So my net force we decided needed to be negative 73.3 newtons. That's got to equal Fg parallel, which is negative 124.25, plus friction, which is positive 106.58, plus the force of Roy. And solve for the force of Roy, and you get negative 213.16 newtons. There we go. All right.